This video is going to be like a quick overview of what the Stream AI project is. I'm going to try to keep it under 10-15 minutes. And yeah, it's not going to be going over any of the code. This is just a high level overview of what's the problem is and how we attempted to solve it. First and foremost is the YOLO model we trained. YOLO is like a state-of-the-art object detection model. Object detection is you give it an image and it tells you where in the image your desired object is, the one you trained it to learn. I gave it, it says 5,000 images in the training set, but I actually gave it around like 2,800 images. I applied augmentations, but yeah, these are details. You don't have to look too deeply into this, but I trained multiple iterations of the YOLO model. I gave it lots of images, and it didn't overfit. It reached pretty good accuracy. I don't have the accuracy here, but the accuracy was around 97% on the testing set. And yeah, I use RoboFlow to collect and process all the data. RoboFlow is this online tool which is you have to pay for, but they have a free trial as well. So I got to use it, and it significantly sped up the process of training the YOLO model. Yeah, and that's the YOLO model, I believe. I don't think there's anything else I need to mention about this. Oh yeah, I have 3 different versions. I might as well note this now because the first version, for some reason, it would think the tip would be like somewhere around here very often. So I had to just give it some null images, some examples of this area, and tell it that there's nothing there. And another time, I realized that the model would, for some reason, think that there would be a tip in all black regions occasionally. So then I also had to give it more null examples of these, empty black images like these, and tell them that there's no tips there. By the way, the tip is, I'm referring to the tip of the extruder, like this right here. This is what I mean when I say the tip. So it's a tip detecting object YOLO model, YOLO V8 to be specific. Okay, now with that out the way, here is the problem we want to solve. Okay, our inputs are, we have the G code, which is the code which controls the printer, right? Tells the 3D printer where and how to move. The video path, so we have a camera recording the 3D printer, and the signals path. And the signals I will talk about what they are in a moment. And our goal is to identify anomalies in real time during the print process. We don't want it just to be video paths and signal paths. We want this to be able to be done in real time with a video streaming in real time. So we made a USB-C connection to the Insta360, which is the camera. We made like a real hardware connection so that the camera could stream the frames to the Raspberry Pi, which we're deploying the system onto, and work with it in real time. And the signals, which I'm about to explain in a moment, we also want these to come in real time. So we have a hardware connection to the SKR board, which is the electrical board in the 3D printer. We made a hardware connection between the SKR board and the Raspberry Pi, so that we can get those signals in real time. And the G-code path is not a real time thing. We have the entire G-code path, the entire G-code file before the print. So that doesn't need to be in real time. So yeah, that's the real time part. And for it to be real time, right, the system needs to be able to keep up with the video, which the video is coming in at 30 frames per second. So the system needs to be able to run fast enough to keep up with that. Okay, now some images just to explain, give you a better idea of what I'm talking about. Here are like some frames from the video. It's a camera looking at the 3D printer from like a point of view. Their 3D printer is printing this thing, and yeah, and these are 3 examples of these are some examples of anomalies. So on the bottom row here, we have normal extrusion. This is no anomaly. This is where the printer is doing a good job. So there's no anomalies here. You can see it's like 2 perpendicular lines. It's doing a good job. Here in this row, the middle row, this is over extrusion. the printer is extruding too much material. You can see there's like a big blob. There's like, right? And lastly, under extrusion, where there's too little material being extruded out of the printer. So normal extrusion, over extrusion, and under extrusion. These are the three classes we have. And the way we're going to try to identify these anomalies is, number one, by trying to use a classification model, so to do classification between these three classes, or secondly, by developing an algorithm to measure the diameter of the recently extruded material. Now, important to note is that we need to look at the area around the tip. Okay? We're getting the video, but we need to focus on and locate exactly where the tip is in the video. And we need to zoom in around there and look at the area, because only the area around the tip, the recently extruded material in the direction of the movement of the printer, is relevant to our decision making. This means, well, okay, we could we could try to make a classification model that takes in the entire image, but there's two problems with that. First of all, a model that takes in an input that big, it might be too slow, and it is too slow to run at 30 frames per second. And secondly, the amount of data we would need to teach the model to, focus in on this specific area and then to do classification around there. We would need lots of data, and we just don't have that amount of data for this project. Collecting this amount of data already took me a very long time, and that's what the anomaly classification repository is for. Okay, so that's why we need a tip tracker to track the tip. Here's what the tip tracker looks like. I'll just skip ahead. So yeah, you can see it's tracking the tip pretty accurately throughout the video. The blue square is where we think the tip is, right? And the green square is the recently extruded material. This is the green square is what we would feed into the classification model to determine whether it's over, under, normally extruding, or on the other hand, measure the diameter of the recently extruded material. Okay, and it is very accurate, very, very accurate. All right, so yeah, now you have an idea of what the video looks like. The other two components, the other two inputs we have the G code up here in the top left, and the signals down here in the bottom left. The G code is quite simple. Okay, so the G code is essentially like listing the coordinates that the printer extruder should be going to one by one. So like it should start at coordinate x, y, and the z coordinate was already mentioned earlier in the G code. It's just not repeating it because it's staying the same. And it wants to move to this coordinate, and it's going to move from that coordinate to that coordinate in a straight line at this given speed f480. So x, y, and z are coordinates. There's no z here again. E is the extrusion speed, so how fast to push the material out to extrude. And F is the speed at which the printer moves at. Okay? Using these, we'll be able to track the tip. And secondly, the signals. These might not immediately be clear as to why they're useful, but they were incredibly useful and significantly simplified the entire process, which I'll explain in a minute. So the signals, this is from the connection to the SKR board. And this SKR board essentially tells us every time it finishes a move. So finishing a move is defined as reaching the end of one of these lines. So when it reaches this coordinate, it sends a signal of that coordinate it reached and the time at which it reached it in milliseconds. So we have this column of milliseconds and x, y, z, the positions. And yeah, so we just get signals coming in every time it reaches a corner essentially. Or when it's going through a curve, it's doing many small line segments, and we get many signals around these curves. Okay? So I'll explain how we use those inputs in a moment. First, let's look at a big overview of this entire system, and we'll go through it step by step. So this is like a visual, which represents the entire system. On this left side, this whole part over here, this is like the initialization and synchronization phase. So since the camera isn't in any strict position, right? The camera might be in a slightly different position every time, might be at a slightly different angle every time. We might be in a different location, and the only inputs is the video, G-code, and the signals. The system, and I did it on purpose because I don't want the people to have to, put the camera in a certain position every time, or to make these measurements on their own, which would be very tedious. I wanted it to be more robust and make it very easy for users to use this system. So it's going to automatically measure some values that we need to track the tip and do what we need to do without any further user input. So this is this whole phase to the left, the initialization and synchronization phase. And then to the right, this whole part, this main thread is like us tracking the tip, and alongside it we have error detection, correction going on, as well as the analytics, us actually looking for the anomalies. So these run alongside each other because the tip tracker has errors. It's not actually perfect, and we need to automatically correct it in real time. So we need these error correction and detection threads running alongside the tip tracker. Okay, let's start by looking at the first step. So the video starts streaming into us, the signals begin streaming into us, and we have our G-code path. First, we want to convert the G-code into a list of predictions for where the tip should be at each point in time. Predictions as in XYZ coordinates on the bed for where we think the tip should be at every frame, every 1/30th of a second. Let's go over the steps for how we do this. I'm not going into too much detail. You can pause the video if you'd like to read it over. But first, we essentially simplify the G-code into just the coordinates, as well as the given speed at each move. Okay. Secondly, we calculate the optimal speed profile. What I mean by this is, for example, if the tip is moving, straight in the y direction, and then the next move is like perpendicular to it in the next direction, that would mean that at the end of this move, the final speed has to be 0. The tip track needs to come to a full stop, and then go to in this new direction. Another example would be like if it wasn't perpendicular, if it was something like this, the tip could move up at some speed, and then it would slow down, and it can retain some speed and continue moving. So we have the initial speed for each move. We by looking at the future moves, we can determine what should the final speed of the move be, and given from the F value in the G code, we know what the max speed should be. We also know from the G code what the acceleration should be. So this is what I mean by we calculate the optimal speed profile for each move, for each line of G code, each motion. Now, given the optimal speed profiles and the coordinates, we can just use simple kinematics to calculate how long each move should take. There is one specific edge case which cannot be solved analytically. We need to solve it using this iterative method, but that's not a big deal. The iterative method is very efficient and accurate as well. So, and yeah, after we compute the speed profile, we get and we know how long the move should take. We just check how much should the tip move per frame during that move, and we can just calculate the bed predictions per frame. So that's not that difficult, really. However, this is not the end of the problem. The problem actually really comes after this now, because this method is not accurate for a wide variety of reasons. First of all, the actual way the G code is interpreted is much more complex than this. For one, and this might be the one of the bigger reasons, is that I'm assuming that the velocity follows a sort of trapezoidal profile, whereas in reality this is impossible. It needs to be continuous. It can't be, have these sharp corners. In the actual implementation, Dr. Zoe showed me in the Merlin firmware for the actual printer. It's this C++ code and it's hundreds of files, and when they interpret the G code, they use Béziers' formula, and they go all the way up to the 6th order of magnitude. So they go beyond acceleration, beyond jerk, beyond, I think it's like pop, snackle, crack, pop, whatever. But yeah, they go to the 6th order of position to more accurately calculate this. And the Béziers formula, it's not too bad. I could add it, but the thing is that's not the only thing. There's more. There's also, there could be little tricks in the G code, and in segmented moves, or when coming to a full stop, there can be these delays or these small differences. And to understand that would mean we would have to go through all of the firmware. But for every printer, the firmware might be a little different. So that would mean we would have to have a custom solution to every different firmware. So rather, let's create a simpler solution. Let's, instead of going too detailed, let's stick with our simple but flawed G-code interpretation. But let's introduce now this like automatic feedback loop that does self-correction, which will in the end give us a more robust and flexible method, and make it easier for me as a coder as well. So yeah, that's the predict bed locations per frame, and I just explained why we need this error detection and correction, because the bed predictions are not accurate. Okay? The next step would be calculating the ratio. When I say ratio, I mean, let me play the video so I can explain better. As you might notice, the tip actually stays in the same Y position on the screen, like the same vertical position on the screen, because the bed is actually moving, if you see it right now. What's relevant to us, when the tip is moving in the Y direction, we can essentially assume that on the screen it is moving, it is staying still. But when the tip moves in the X direction, we know from our bed predictions how far it moved in millimeters, but we need to know the millimeters to pixel ratio. That is what I mean by the ratio. It is the millimeters to pixel ratio in the X direction on this specific height, I guess, on the screen. And once again, as I want to make the system more adaptable, or what's the word? Flexible, less strict, less rigid. I don't want to force people to put the camera in the same position or the same angle every time. Let's automatically derive the ratio just using our YOLO model. So what we can do is, using our signals, so there, for example, there would be a signal here and a signal here, because this is the start of a move, and this is the start of a move. Okay, so we would get the XYZ coordinates here and the time, and the XYZ coordinates here and the time. At this moment, when the tip is over here, we can run YOLO. My YOLO model, I forgot to mention, takes in a 640 by 640 input. So we'd actually need to slide across the entire image and see where the tip is. And we can locate the tip on the screen, and we also know where the tip is on the bed for that frame. And then we can do the same thing over here. And then it's just a simple matter of getting the millimeter difference and getting the pixel difference and calculating the ratio. Okay? Alright. Next step, we need a place to begin tracking from. So we don't know where the tip is on the screen. But from the YOLO inference we just made, we know we have a good starting point. We can start tracking from where our first YOLO prediction was, and then use our bed predictions interpolating from there going forward and begin tracking. And next and lastly, before we move on and finish the initialization and synchronization phase, is to convert the bed predictions into screen predictions. Because right now we have predictions for where the tip should be on the bed in X, Y, Z coordinates for every frame. But we need screen predictions in X and Y. We need to project those bed predictions into screen predictions. Okay? It's quite nice because, as I mentioned, the problem is massively simplified because the tip only moves in the X direction because the bed is moving for the Y direction. And so we only need to consider movement in the X direction. Okay? And we have the starting point. We have a starting pixel point and the signal that we can begin from. So that's what I've labeled the first YOLO. The first time I used the YOLO model. So we can begin from that point. That can serve as the synchronization point between the physical world and the camera's view. Okay? And then it just goes like this. Looking at bed predictions, the bed predictions say we move this many millimeters for the next frame, and we move this many millimeters for the next frame. All we do is we use the ratio, right? We only care about the movement in the X direction, and we use the ratio to convert that movement in millimeters to movement in pixels. And yeah, we can transform all of those bed predictions into screen predictions. Another thing to note is when a tip moves up in the Z direction, as you're about to see right now, in that very, in that very small moment, the tip actually does move in the Y direction on the screen. For that, we have what are called spatial threads. Spatial corrections, which I'll talk about later on. Okay. So yeah, now we can begin tracking. We can begin tracking, and we can begin running all of these threads alongside the tip tracker. And by the way, all these threads share these global variables together. And these threads can correct any mistakes in some of these threads if there's like mistakes and stuff, which is their purpose. Okay. So first, let's take a look at the ratio thread. So as I just mentioned, the tip occasionally moves up in the Z direction. And when the tip moves up in the Z direction, this is a very small movement in the Z direction, but imagine the tip had moved like much higher in the Z direction. The ratio would change. The ratio thread's purpose is essentially just whenever there's a change in the Z direction, recalculate the ratio. That's it. Okay? The spatial thread, which I mentioned earlier. This is a demonstration of what a spatial error is. So there's an error in some amount of pixels in spatially, and it's constant. That's crucial. It's a consistent spatial error, and that's a spatial correction right there. Okay? The way this works is very simple. Signals come in. For example, that was the start of the move right there. A signal came in. The signal told us where the tip actually is on the screen. And we have the prediction. This is our prediction of where the tip is. And we can just do some simple arithmetic. There's an error there. Okay? Tip continues. There's another signal right here. This is the start of a move. The YOLO model tells us the tip is over here. We think the tip is over here. Another spatial error. And it's the same spatial error once again. And this continues. When we collect enough spatial errors that are the same, we can confidently say that this is a spatial error and make a correction, as seen right there. Notice that it has to be a consistent spatial error. Okay? Okay. Oops. Oh yeah, right. Alright, next is the temporal thread. Okay? Just take a look here. This is temporal error. A demonstration of what temporal error is. This is why I said the spatial error has to be consistent. Here you can see the tip tracker appears to be behind by a few seconds. And the spatial error is changing. The way we can detect temporal error is by this. So right here, this is a curve, so it will actually be a bunch of signals will be coming in at this time, and those signals would tell us the time at which the move finished or started. And we can just look at our bed predictions and look at when we thought those moves were supposed to finish or start. And we can simply calculate the difference in seconds or frames. And that's the time error. Okay? And if there's a consistent temporal error this time, not a consistent spatial error, consistent temporal error, so consistent, like the tip tracker is consistently behind the actual tip by like 2 seconds, let's say, then we can simply just readjust all of them by that time. We don't actually just like shift all the predictions. Instead, what we do is, to make the transition more smooth, is if we're ahead, we can add some buffer frames in between, or if we're behind, we can just remove some of the predictions so they can catch up quickly. Okay? Now, once again, I said consistent temporal errors. In some cases, we don't have consistent temporal errors. These top two graphs here are plots of temporal errors or offsets versus time. Temporal offsets are in seconds here, and the x-axis is frames. These two graphs are just two different examples with two different inputs. What's happening here is that the actual acceleration value is off. Okay? So the temporal error is increasing as the video progresses and getting worse. So what we need to correct here is the acceleration value, and we need to recalculate the bed predictions from the G-code. Note that there appears to be two distinct lines with different slopes here. This comes from the two different parts of the print. The first part of the print has these contours, and it never comes to a full stop, whereas the second part of the print has many full stops and these straight lines with no contours. Note here, you can see that the tip has fallen much more behind. This is an acceleration error. The temporal error is getting progressively worse and worse throughout the video. So yeah, this is kind of strange, but this is what I meant when I said that there's more to why the bed predictions were wrong than just the us missing the implementation of the Bayesian formula. There seems to be, during contours or during full stops, there's other little tricks in the Merlin-Fermer interpretation of the G-code that causes these differences. Luckily, looking at the slope of the line, the slope of the line tells us how much we need to correct acceleration by. It's a quadratic formula, and I derived it using empirical evidence. I just tested many different inputs, and I saw that there was a clear pattern, and I just made the equation. I just plugged in A, B, and C, and that was it. We do need to account for this change in slope, this moment of change in slope. So as you can see, the slope here follows this curve because we didn't separate these two lines up. It shouldn't be this curve. It should be like two distinct different slopes. So what we have to do is piecewise linear regression to split up the temporal offsets versus time into two different sections. Okay? Yeah, so that's acceleration correction. Just to review, that was a lot. Don't worry too much about the implementation. All of this works very well. I'm just explaining what I did. So you won't need to change any of this code. We have the spatial errors, which is some error by some amount of pixels. We have temporal errors, so we might be off by some amount of seconds, or we might be off, or the temporal error might be getting progressively worse throughout the video. So we need to change the acceleration. Okay? And the ratio thread, of course. Now we can look at, lastly, the analytics thread. the analytics thread is where we actually achieve our goal. We do analysis where we have our tip tracker, we have our nice error detection and correction going on, so we know that our tip tracker is performing well. So we know exactly where the tip is, and we can do some analytics on that green box. The first technique we applied was using classification models. I didn't want to train a model from scratch because we don't have enough data for that. So we're going to try transfer learning and fine tunings on some of the best models, open source models out there, which is MobileNet here, ResNet, and EfficientNet. ResNet creates residual connections between different layers in the network. So if there's like a very deep network, there can be connections going in so that the loss can get back propagated deeper into a model without that vanishing gradient problem. Or, if you try to counteract the vanishing gradient problem, you might have that exploding gradient problem. So we just avoid that problem altogether, and we have these residual connections. The MobileNet model has a few really cool things about it. First of all, there's this efficiency optimization where I don't exactly remember, but instead of doing this depthwise convolution in 3 dimensions, it splits it up into a 2D and a 1D depthwise convolution, which speeds up that particular step in the convolution in the network exponentially. It also uses, typically, we experiment to find the right hyperparameters. They used neural architecture search to find the best size, the best hyperparameters, all the hyperparameters for the neural network, which is very, very cool. That's something that I've always been interested in. And lastly, well, there's more, but they also have this thing, which I didn't look into that much, which allows the MobileNet to somehow adapt to different mobile hardware. So if you want to run MobileNet on a mobile device, like a Raspberry Pi or something, MobileNet can adapt and become more efficient on the device. I'm not sure how that works, but that's very useful for us because we're using Raspberry Pi. We want to deploy this to the edge. And the EfficientNet isn't as interesting. They essentially made a model, and they made one very good model, and they discovered a technique to scale the model in width and height, like making it deeper or making larger inputs. But EfficientNet, one of the more popular models, so I decided to add it to my arsenal. So I experimented with all of these models to try to figure out which one worked the best. These are the data pre-processing steps I ended up finding to work the best. This is how many images I had for each class. I cropped images at 85 by 85 because the reason for that is 85 by 85 is the green square. That's just the perfect size to get the relevant information. That's the area around the tip. That's the recently extruded material. So that's why there's a reason I chose 85 by 85. But we want to resize the images to 224 by 224. It doesn't improve resolution. The images, there's no more information gained by doing this. The reason for doing this is that all these models were trained on the ImageNet dataset, which that dataset had images at 224 by 224. So these models have learned features at that scale. And I experimented. I tried training these models with this sized inputs and these sized inputs. The 224 by 224 inputs clearly outperform inputs of this size. So we resized all images to this size. Additionally, there's a pre-processing step, which I tried sharpening, sharpening filters and all of these filters. They didn't work, so I had to create my own custom pre-processing filter step, and I'll explain that later on. And for the dataset, I applied augmentations using all these very basic techniques, and this is the split: 75% training, 15% validation, 10% testing. Okay, yeah, these are the best methods. I experimented across many different methods. I trained hundreds of models to find that these worked out the best. This is the whole data pipeline. Collecting the data was very slow. I collected the data without using the tip tracker. I initially did it manually, but I made some, small scripts to speed up the process significantly. I started my video. I have this little interface to select the frames that are of interest, so under or over frames, the anomalies to find them. We apply grayscale, black and white it, crop it. I created another little script to speed up this process to crop out the relevant part. Apply the preprocessing step. This is what the preprocessing looks like. Resize to 224 by 224. Data augmentation. Split into train, test, and validation sets, and then you can train the model. That's your data set ready. This is the whole data pipeline right here. These are the training hyperparameters or techniques that I ended up using. Fine tuning ended up working better than transfer learning. I tried both out. I guess our problem is very different from the image and data set. The image and data set is like more like regular pictures, I guess you can say, like of people and nature and outdoorsy stuff. Whereas our picture is like a very zoomed in picture of this tip. So transfer learning, where we just tweak the last layer, didn't work very well. We kind of need to fine tune the entire model to because our task is very different. I introduced model checkpointing to get the best model. More batches turn out to work better because we have less data. 12 epochs, just looking at these graphs, you can see that the metrics seem to flatten out pretty quickly around like 12 epochs. Actually, around like 10 epochs. I said 12 epochs to be safe. I introduced learning rate decay and early stopping to avoid overfitting. Luckily, this graph looks pretty, it's like a lot to take in, but the only relevant thing to see here is that we achieved an accuracy of like above 90%, and there's no overfitting, because if you look at the validation metrics versus the training metrics, they nearly match each other perfectly, which means that there's no overfitting of any sort, which is what we want. Okay, now to talk about that pre-processing step, that filter I mentioned. First, I tried applying like basic filters, like blurs and sharpen things. I just found out that this didn't work. Different images needed different combinations of filters and was not going to work at all. I made another custom filter step, kind of, which looked at the standard deviation of the pixels in the image. So if there was more deviation, like in this one where there's like black and white, then I'll be less sensitive. And yeah, or if there's like a lot of white, I'll be more sensitive. But this didn't work. As you can see, there should be a line here, but there's no line there, and there's like two very faint lines here, but the filter didn't catch that. I also tried using these pre-processing steps from CV2 and PIL, the popular libraries. Also did not improve the quality of the images at all. So what I noticed is that I actually noticed this myself. So apparently this is a very popular technique, but I'm very proud of myself because I actually came up with this myself. It was an original idea of mine. If you look at each image, first of all, these should all be black and whited, but they're not, but it doesn't matter. Each of these images have like around 5 to 7 different like colors in them. There's like the color of the tip's metal, there is the glare in the tip, there's the material, sometimes there's a glare in the material, there's the shadow around the material, and there's sometimes a bed, right? And there's like background material, so there's material in the background. Okay, and each particular color, like the color of the bed, all of the bed follows this like normal distribution. Like the color of the bed has like a mean value, and it has like the standard deviation in both directions. So each color, like the tip, the material, has its own little normal distribution. So these plots down here are pixel intensities versus how many times they appear. Like you see in this one, there's a lot more dark colors, so we have more pixel intensities in the darker regions. Around 0 is black and 255 is white. Whereas in this picture, it's a lot of white, so we see lots of count in the brighter colors. essentially we can apply a Gaussian mixture model to, right? So like this black dotted line or this red line would be what our actual data looks like. But underlying that data, we have these separate normal distributions. The way this model works is that we have to tell it how many how many distributions we think there are, and it will find those distributions for us, the standard deviations and the means of those distributions. Okay, so I try this technique using different numbers of assuming different numbers of clusters. I mentioned that usually there's 5 to 7 colors in the image. So I mean I tried 8, 12, and 16. You can see that at this point it begins getting a little too much noise here. But amazingly, the filter actually worked. So this is like a very faint image here. You can barely see the lines. But I mean here too. But the filter clearly brings out those lines there. And that's exactly what we wanted. I was actually looking at this image when I was trying to figure this out. I started going a bit crazy because I wasn't even sure if there really was lines there. I was starting to like second guess myself and thinking maybe there aren't lines there at all, but there were lines here, and this made me very happy to see the filter finally work. I added a little more customization. So for this particular problem, we want to be more sensitive with brighter colors, with more white colors, because white means that there's like stacks of layers of material on top of each other, and we need to be much more sensitive with white colors. So I essentially customized the algorithm a bit more to be sensitive to whiter colors. In GMM, the Gaussian mixture model, assuming 6 clusters, works the best. By looking at it and also by testing it with the different models I trained. Okay, so here's looking at the data pipeline one more time. We apply the Gaussian mixture model plus sensitivity filter here, and yeah, we use the model to identify over, under, and normal class extrusion. That's our analysis. We also have let me skip forward first. We also have the other method, the measure diameter method. I just haven't finished doing this correctly. Essentially, the way it works is we know the direction that the tip is moving it from the G code, so we can take lines and just shift them throughout the image and find the best location. Also, these images are not using the Gaussian mixture model filter. This is using the other filter I made, the custom one, using the standard deviation of the image. But yeah, I need to make this step better, because right now it doesn't work very well with under extrusion or over extrusion. It works well with normal extrusion, but yeah, we can just look at the distance between these two lines and use the millimeter to pixel ratio to calculate the millimeter difference, which is the goal. Okay, and here's a demonstration of the tip tracking in real time alongside classification. So here it's giving constant classifications, and you can see it's making mistakes. The data I collected manually, I guess is a little different from the data here. And there's also times where the tip is like, for example, going down here. So in these situations where we can't even see the material, we can just I can add a little thing where we just give up and we can't do a classification there. We need a different camera angle. We can't get around this, but we should be classifying these correctly. This should be normal. I mean, it's saying normal now, but it does make mistakes. Normal, over. That was not over. At that very edge right there, at the corner, it saw over, I think. Yeah, so this is what we need to solve next. We need to collect data from the tip tracker, from the actual tip tracker, where it makes mistakes, where it goes wrong, and collect that data and feed it back into the model so that it won't make mistakes in these situations. So basically, we just need to improve the MobileNet model accuracy. Okay. Yeah, and I was going to add some errors I encountered throughout. There's like a ton of tiny little things that made this project much more difficult. But I was going to list them out, but that's all in the past now. So another thing I want to mention before I finish this recording. I hope the recording wasn't too long. I think that recording was pretty long. Just like a little excuse for myself. So this project took me. It's been like 8-9 months. I took like gaps in between. I was doing it during school, but just until last month, I was doing this whole project without the signals. Um, Only last month, or a little more than a month ago, did Dr. Zoe implement that hardware connection to give me the signals. And before that, this was like this whole problem was like way more complicated and difficult. But the signals came in, it was like a blessing, and it simplified the problem so much.